Accountability. Wow, this is going to be fun. Okay. So in this chapter, generally what he's trying to do is tell us about model selection and the metrics we use for model selection. Specifically the in-sample error, we talk extensively about that, and then we go slightly into model complexity and what happens when we increase or decrease model complexity with respect to the in-sample error. So I mean that there's almost zero involved math here. It's basically language, and I've highlighted the important takeaways. There aren't any proofs as far as I can tell, so we can breeze through this fairly easily and stop wherever you want to discuss something. I was very proud of myself for building this summary. Then I realized he's already explained it in these terms. So yeah, there are three ways we can use statistical models in data analysis: as summaries, that is to describe the data, as predictors, which is to infer from the data, and as simulators, which is to sample data. And he steps through these as not a option 1, option 2, option 3, but rather as a stage 1, stage 2, and stage 3, with explanations of why we like motivating why that particular property is useful. So he starts with the least demanding use, which is to summarize the data. So you want to be able to if someone asks you about your data, you want to be able to explain it in a sentence, not by showing them a scatter plot of how the data is distributed and what those individual data points are. You want to be able to have summary statistics for it. An explanation of this is, rather than remembering all the points on a scatter plot, we just want to remember what the regression surface was. So what the line passing through them, or the surface, higher dimensional objects. It's a summary. He slightly implies that a summary may just lose us some information, but we aren't relying on any assumptions in making that summary. At least when those assumptions come in is when we make predictions. So a prediction is essentially extrapolating that summary to a new point where we don't really know about the correct answer. So that is your prediction. So when you start to make predictions, you run the risk of being wrong. And what else do I want to say about this? Yeah, the assumption behind this whole learning process is that our mistakes with the predictions will follow a pattern that is stable enough to tell us more about the world. Obviously, the end goal is to learn more about the world, not just the sample, but the population. And the inherent assumption is that there is an underlying pattern. We just don't have complete knowledge of that, and we want to have knowledge of that. If there is no underlying pattern, then by definition we are not going to be able to learn anything about the world. So that is a philosophical argument to be had. But yeah, for the purpose of general application, we assume that there is a pattern, and it turns out that in a lot of cases there is a pattern, and we're reasonably able to capture that well. And stepping from prediction to the next stage, what we want to do is we want to see how well this model captures the real world, and predictions are one way to go about it. But if we truly believe that that model reflects our understanding of the world, then it should be able to simulate this world. So if these models are accurate, so statistical models become stories about how the data was generated, and if they're accurate, we should be able to use them to simulate that process, to step through it and produce something that looks probabilistically just like the actual data. And that's where your scientific model comes in rather than just statistical ones, because in a scientific model there is some underlying causal structure, and again we'll get back into that later when you come to causal inference. But he gives a nice example that okay, there are two models at least of the universe where one is the earth is the center and the sun is the center. You can learn something in both cases, but in when you assume the earth is the center, those parameters won't mean anything, um, because the true model, or at least the model that we know to be true, um, is that the sun is at the center, and therefore if you have Mars moving at x meters per second, in that model it actually means something, whereas in the earth is at the center, that Mars is moving somewhere, but that orbit is not necessarily, well, it is well defined in a sense, but it's not the accurate one. Like, that's what he's trying to say. Okay, so this chapter focuses on evaluating predictions for three reasons. Oh, hi, Sharmishta. Let me summarize what I was saying. Essentially, this chapter has no involved math, so we are on good. We're on steady ice in that on that front. So it won't take a lot of time for this session, is what I meant. So far, three things came up. When you what like the motivation for using statistical models is to describe the data, to use those descriptions to make inferences from data, and to be able to test that inference in the real world by trying to sample and seeing how those samples measure up against real data. So that's about it. It's just been like 3 or 4 minutes. Okay, so with when we talk about errors, we generally talk about in-sample error, because you don't typically measure out of sample error. You talk about we have spoken about in-sample error so far, and we train using in-sample error. Um, I'm getting ahead of myself. Okay, what is he saying? Yeah, I mean, we want to minimize in-sample error. If it can't be small all the time, we'd at least like it to be small on average. We also want the errors to be patternless by definition, because if there is a pattern to the errors, then why aren't we learning it? Yeah, we'll come back to patterns later. Yeah, that's fine. Just to set some terminology, m theta of x, m subscript theta of x is the model, is the regression function, where theta is the parameters and x are the data. Z are the data set, so the data point z is equal to xy, and L is the loss. The mean squared error, L is y minus m theta x the whole squared, and the mean absolute error is mod of y minus m theta x. So he just explains we can use different kinds of losses, but in general we will define our loss function as L of z comma theta. Now if we had like a probabilistic model, then we would get a distribution for the data. So at a new point z, this p theta would be a probability density at z. So and the loss function would be the negative log likelihood. So essentially he's giving an example of, again, um, he spoke about different kinds of errors and different kinds of models. So that's it. No matter what the loss function is, he abbreviates a sample average of the loss over the whole data set by this L bar. And ideally, we would like a predictive model with zero error on future data, which obviously we basically never achieve. I mean, you should be really suspicious if you get that model. Well, on future data, not so much. You should be suspicious if you get that model on training data, because that probably means you're overfitting. Yeah, that's a fair statement to make. The reason I corrected myself is because if you get zero error on future data, that means your model is perfect. So that's good. But if you get that on in sample data, then that means you're only optimizing for the sample you see, and that sample might not reflect the population, which is actually a discussion that we've been having for the past week on the Slack channel, that sample versus population means and variances. Yeah, so just general observations. World is a really noisy and stochastic place. If you go back to the first chapter, the bias variance decomposition, your expected value of the mean squared error for a particular estimator over all the data has this term which is fixed. Like, we can't, fixed in the sense not the same value but a value. Like, there will be that term. Even if you optimize and reduce, you can't optimize and reduce both other terms to zero simultaneously, but even if you optimize for these two, this term will be there. So that's a statistical error or inherent randomness in the world. Another source of your errors is that your models are usually more or less misspecified, or in plain words wrong. Or degree of being wrong is different, but it is very, 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 very hard or impossible to get the functional form of the regression, the distribution of the noise, and the form of causal dependence exactly right. So yeah, this is the origin of the bias term in this decomposition. So the second term, that is where your assumptions about the world might be wrong. And finally, your models are never perfectly estimated. There is some finite sample size, so you don't have all of the data you need to estimate. And this is the origin of the variance term. Of course, as you get more and more data, this should become less. But because the bias term will almost in theory, if you have the most perfect model and you have infinite data, then you can make these two go to zero, but this term will still remain. And again, that in theory is a stretch. Like, I shouldn't be saying that because that is probably mathematically inaccurate. Yeah. But so, because we can't in practice push all of these terms to zero, what we try to do is we would like to minimize the expected error or risk or generalization error on new data. So this is just a mathematical formulation. Your expected value of that loss on all data z and parameter sets theta is what you would want to minimize. To prove this, however, we have to calculate that expectation, and you don't know the true joint distribution of this LZ theta. It is also very hard to calculate that overall theta and overall z. So a natural approximation is to use the training data Zn, and then for each model that we have, we can calculate the sample mean of the error called the in-sample loss, and then pick the model that best minimizes this loss. Again, it is important to note that these mathematical formulations will be used later on, so it's better to familiarize ourselves with it. Hat, basically, in general, it implies the estimates. L bar generally implies means. I mean, we've been through this, but I'm just reiterating for someone who might have missed out. Yeah, so the best estimate is the one that minimizes. Argmin is basically the argument theta that minimizes this term. I actually learnt about this last year, so I was aware that this exists. I just never thought deeply about what exactly I'm doing. But yeah, it's interesting. It's important to drill down those things because they appear and people often don't explain what they mean. So yeah, the argument that minimizes this term, theta. This means picking the regression which minimizes the sum of squared errors, assuming L refers to the squared errors in this case, or the density of the highest likelihood. these both imply the same thing. um, this is what you usually done, and it is very natural, but obviously it has two problems: optimism and overfitting. And then the following sections will highlight what we mean by optimism. Optimism refers to the finiteness. Training data isn't perfectly representative. Um, by the law of large numbers, this does converge to the expected value. So the in-sample loss will converge to the expected value of the loss overall, models and data, as we get more and more samples. This means with enough data, the in-sample error is a good approximation to the generalization error of any given model theta, because both of them converge to the same value. Or in other words, big samples are representative of the underlying population, so the error on the population will be the expected error. But this does not mean that the in-sample performance of this estimator tells us how well it will generalize, because we purposely tricked it to match the training data Z. To see this, notice that the in-sample loss equals the risk plus some sampling noise. Now the sampling noise he explains as eta of n. So there is some inherent stochasticity in the sampling procedure that results in some noise. That's what he's saying. And more importantly, this will be different for each theta. Like the way you do this will affect the model parameters in different ways. So already said this, it's a random term which has mean 0, so the expected value is 0. And yeah, it's the error due to finiteness, the finiteness of data, rather than the complete probability distribution. And different values of theta are going to be affected differently by the same sampling fluctuations. So by that definition, when we minimize this term, when we are saying argmin of the average in-sample error, that could mean that this is huge and this is huge, but in the opposite direction, and therefore they cancel each other out. But that doesn't mean, obviously what we want to actually minimize is this quantity, but this quantity might actually end up being huge, and we pick a lucky case where this is equally negative, and therefore we assume this is minimized, but because we only see the total term. So that's what he's trying to drive at, that just because this whole term is small does not mean this term is small. So we only want to minimize the expected value of the loss of the error, but we can't separate it from the randomness. So we are almost surely going to end up picking an estimator which was more or less lucky as well as good. So he's not saying that this is the worst case is what I described, but in on average it's going to be, this is a small negative value, a small positive value, but it won't be that this is like, you can't get lucky enough in general to get the actual minimum of this. And that's what he drives at in the graph that follows. That okay, this is the true MSE from the true model on the data, and this is the empirical MSE from the model we assume on the data. So there is some bias term, and therefore the minimization will also give us some difference, and this difference can be categorized as the gap between the curves is the eta of n, which varies with the theta. As you can see, like based on whatever model you assume in black, this curve will shift. So this this sample random term, whatever, will vary, will have a different impact on each theta. That's what he's getting at. Now, yeah. That's a good question. Let me see. The x-axis is the regression slope. So this is the value at which this is minimized. I think you might be right. Yeah, the MSE risk gap between the curves is the x eta, the MSE in a particular. Sorry, did I say that this is the. No, I wrote this correctly. I think I wrote this correctly because this is the I wrote the minima, so this is the theta that is the minimum for this curve, and the risk that you're talking about um, changes as this. So the risk, yeah, the difference in let me write. I can't write. Maybe I can write. So what you're saying is the difference in risk. The minima term is that is the difference in minima, and this is the difference in. No, not that way. I should draw it this way. Yeah, this is the difference in MSE risk. I think what you were asking was this is the difference in errors at the same value. Yeah. Cool. So, yeah, I just to clarify the explanation, in case I explained it wrong the first time, I don't remember what I exactly said, but um, they're saying that the points the points I plotted here are basically that the minima is at different points, and if you consider the same point, there will be a difference in the risk for the true model versus this model, and that is your eta of n, which will vary with the theta, because again, if you assume a different curve, for example, if you assume a curve like this, then there will be a different you understand that this vertical difference changes with that curve, so it will become like this between the gray and the orange curve. I hope that's clear. Cool, thank you for pointing that out. Okay, and then he makes some comments that okay, we want to also be able to know how fast the eta converges to zero, um, and we can do that by knowing how fast the maximum value and the minimum value of the eta goes to zero. Max mod is basically like upper bound and lower bound, um, and that allows us to basically allows us to make stronger claims about convergence on the true risk. And yeah, there is a lot of theory about this, obvious reasons that you want to be able to like empirical risk minimization. um, I would say there are different, like we broadly cover a lot of theoretical ground by saying machine learning, but this is actually statistics. Anyway, um, the second this is about the second part of these two reasons that he gave. Where was that optimism and yeah, the it's we picking this model as two issues, optimism and overfitting. So we covered optimism, which has to do with finiteness, and the eta, and now we're going to overfitting. How much time? It's 12:07. I should be able to do this in 20 minutes. Okay, the big problem with using the in-sample error is related to over-optimism, but also more important is the problem of overfitting. And we've all heard about overfitting, so let's get into the details of what this is and see an example of how it affects the error, the in-sample error. So here we work with the assumption of a particular model. The two regression curves are parabola with additive and independent Gaussian noise. Now we are fitting different degrees of polynomials. So you fit y is equal to mx plus c, y is equal to ax square plus bx plus c, y is equal to cubic cubic. What is a degree 4 polynomial? Is there a term for it? Degree 4, degree 5, whatever. And he shows that on the plot later. But generally the idea is that the in-sample error goes down as the degree of the polynomial increases. It has to. Why is this statement here? It has to, because every polynomial of degree p can also be written as a polynomial of degree p plus 1 with a 0 coefficient for the p plus 1th term, degree term. So what he's saying is, if you write ax cube plus bx square, I really need to figure out a better way to do this, plus cx. This cubic also involves like the quadratic model, like covers all quadratic models and covers all linear models. Because if you just set a and b to 0, this cubic now becomes a linear model. If you set a to 0, this cubic now becomes a quadratic model of any form. This is a general form, because quadratics are also ax square plus b plus some constant, but I'm ignoring that for now. Anyway, so that's why higher degree polynomials are more powerful or have more capacity, he says somewhere later. But yeah, that's the idea, that okay, more powerful meaning it can fit data better. I can't fit one line to pass through these 3 data points. I can fit a parabola to pass through this, but then if I have a 4th point, then I can't fit that. But then I do have a cubic that goes something like this, right? Just a representation, but hopefully you see the point. Just to be more precise, might be able to. Well, actually it shouldn't have mattered, but okay. But I can fit a cubic that goes like that, and then fits all of these 4 points. Anyway, the idea is, if you have p points, and if you have p points, you need a p minus 1 degree polynomial to fit it completely. So what are we done here? Like, if you have p data points, just assume a p minus 1 polynomial, you will fit the data perfectly, your error will go to 0. And there you go, machine learning done. Not exactly. We minimize the in-sample error, but we did not look at the generalization or out-of-sample error. And that's the basic idea, that when you take more complex polynomials, you might do well on the data, but that's probably because you're overfitting. And that means he just goes on to show, what was this diagram? Scatter plot showing the sample data and the true quadratic regression curve. So the true model is quadratic, and this is the regression curve for the data. Why does he say true? Because then all of the points should be lying on the data. Right, yeah, good point, yeah. Okay, so then he takes more complicated ones and fits them through the data, and it turns out that okay, it can fit the data well, but when you look at generalization error, that's where you're going to mess up. So yeah, I'm not dwelling too much on that. He raises the point again. This is the same point being reiterated, that okay, for models with lower degrees, lower models that are lower degree polynomials, in sample error is much larger, and this is an exponential scale, so definitely much larger than, so logarithmic scale. It doesn't change the point. Okay. And okay, yeah, he's just trying to show the difference between these. That's a logarithmic. And as you increase the degree of the polynomial, initially there's a drastic drop in sample error, and there's slight drops. So also, as a side note, maybe when you see a drastic drop, that's the right point at which to stop optimizing. I don't know, maybe that's some theory to do with that, but interesting to think about it. Yeah, the model which does best here is quadratic, because the true regression happens to be that form. Okay, yeah, he is saying maybe that's correlated, maybe I'm just looking at, I think that's correlated. Initial large drop indicates that you are approaching the true model, and then small drops is basically, okay, you're just learning the noise, which is not good. Learning the noise is never good. That means you're optimizing for random patterns in your data, and by definition those patterns are random, so when you're out of sample you're going to not do well. In terms of our earlier notation, eta is bigger for the more flexible models. Is he talking about out of sample? That would make sense. Yeah, anyway, we covered the point. Yeah, the bigger models were doing better on the training data, but that just meant they are matching the noise better. In general, in terms of the bias variance decomposition, bias shrinks with the model degree, but the variance grows. What that means is basically if ax cube contains a lot more models, so it is less biased, but it also contains a lot more models, so it has a lot more variance. When I say less biased, it means it possibly contains the true models. At least it's more likely to contain the true model than a quadratic. In this case, quadratic is the true model, but yeah, in general we don't know what the true model is, so we just assume that okay, the more complicated we pick a model, the less bias we have, but then we also have to account for the increasing variance. And yeah, in general this is just explaining the same things in more detail, so you can go through that. How am I doing on time? Okay, 10 more minutes, I should be able to cross validation. Okay, so we learned that okay, it's not a great idea to just use the in sample error to measure it, so then what can we do? And the the solution seems pretty simple. Generate more data from your true model and try to evaluate your models on those additional data that the model hasn't seen. And okay, in some cases you can do that, but in all cases you won't have the luxury of being able to get more data. So what you do is you split your original data, keep some aside, train it on the rest, and test it on that new data, because essentially it's the same thing. That new data is data from the true model. And now, because this data has been kept aside in the same way for all your estimators, it won't be dependent on the theta. So this is an independent term, and because of that, now when you compare models, you will have a much better indicator of generalization performance than you would have had before. So this procedure of keeping data aside and testing on it is validation. And there are different ways to do validation. One way is just pick a random sample, validate on it. But there are better ways of doing that people have created, and we'll get into those. one thing you need to remember is you cannot use any of the validation data in estimating the model, because then you're creating a dependence between your estimator and your validation data, which has this sampling error associated with it. So the entire reason this worked was because this term is now independent of theta and theta hat, and um, if you create that dependence, then you go back to the previous case where you can't assure that this is less and that is high and so on. So yeah, this that's validation, and we were talking about more innovative ways of doing validation. So if you just look at this diagram, it represents what k-fold cross validation is. So originally we said, okay, we'll keep aside this set of data, but what if you repeat your model training 3 times and take individual rows of or columns of data aside, and then do the same thing and then average the error across those. And the general idea is that is a more robust way to estimate your validation error, because it avoids there might be some bias in the way you're selecting your validation set, and at least that avoids that sort of it averages out that sort of effect across all of your data. Or again, there is always that you might just have gotten unlucky, and repeating your procedures n times or k times with different subsets of the data gives you a better estimate. I need chai at some point. Fuck. He repeats the same point in general. Randomly dividing it into training and test sets makes it very unlikely that the division is rigged to favor any one model class over and above it would do on real new data. Fair enough. No very important points that I want to highlight. Other than that, there are circumstances where it can fail, especially if you give it too many models to pick among. And again, too many model means some model will optimize for your k-fold procedure and do very well on that validation, but fail in the real world. And there are a number of reasons it can fail, not just one, but yeah. He describes an alternate procedure and says why what he's described in the main text. Make sure that each point is used in the test suite just once. You can see from this diagram, I tried to make it fairly obvious. And yeah, I keep a running version of these notes on Google Drive. I think I've shared the link, but I'll share it again just in case. Leave one out cross validation. This is in principle the same idea, but instead of k sets you now have n sets, because your size of each set is just 1 point. So you do this for each individual point. And I'd actually missed some understanding here, partly because I didn't spend enough time on it. But he says it is less biased an estimator of the performance of a model trained with all of the data points, n data points, than is k-fold cross validation, which uses k minus 1 by k times n data points. That is fair. I understand it is less biased because it has more data. Because earlier we were leaving out a whole row of data and training it, so obviously the sample size was smaller and therefore bias was higher. Is that fair to say? Need to think about this. I will. Okay. What I'm really thinking of is that he mentions this statement, because we're only testing on one data point, it's often possible to find what the prediction on the left hand point would be by doing calculations on a model fit to the whole data. So the way I understand this is, why would you want to do this? Because if you want to see that if you leave out this 1 point, does the model change dramatically, which is usually not a good thing to see. because you want your model to generally be well, would do well. Like you don't want one data point to influence the model all that much. So yeah, I my understanding was this, but I don't know if that is how he thinks about it. And he also says this means that we have to fit the model only once rather than k times, which can be a big saving of computing time. And I don't completely get what this means. So if someone could step in and explain, I would be very happy. Mm-hmm. Remove the prediction for one. Right. Okay. Okay, so uh, just in case the screen recording doesn't capture my audio, what Fennel explained was that what he shows in the section on linear smoothers is that you just have to fit the model once to all the data points, and then you can remove the effect of that last data point from that model. So effectively you're not retraining, but you just have to do that last procedure of removal, that effect of 1 point, and therefore he says that you save on computing time because you don't fit on the data k times, which seems fair. This seems like the right explanation. Yeah, so then he compares k-fold cross validation with leave one out cross validation, and obviously you use more of the training data in leave one out than in k-fold. So that means more of the data is shared between two estimators. Basically, you look at the overlap between the colors in both of these, and there is more of an overlap in orange here than there is here, and therefore these two models are less correlated than these two models would be. And that more correlated basically means you're not doing all that different and you're trying to still test performance, so there is still some sort of drawback, which is why in general it is a subordinate. Like leave one out as a subordinate to k-fold because of the fact that models you're learning are very correlated. And yeah, we kind of covered this, but he explains a shortcut to linear smoothers where you go back to your equations and you look up that you're learning some sort of W for called the influence smoothing or hat matrix. And then he says what happens when we hold back a data point I and make a prediction. Sorry, my throat is just giving up on me. Okay, my notes are off now. Beautiful. But in general, this is the equation you want to see, that okay, leave one out score is basically this whole model. Well, he develops it, so these are essentially the same equation, but yeah. Not the same equation. These two are the same equation, and this is what we do in leave one out. But this explains why in leave one out you don't have to retrain the model each time. Like you have the same W and you work with, you do some linear algebra, but you don't have to do all of the regression training. Yeah, after this point I didn't actually go through it in a lot of detail, so if someone wants to step in and summarize the last 2 pages, then that would be awesome. Okay, in that case, let's take a look at what he's saying. All of the model selections I've described and almost all others aim at getting models which will generalize well to new data if it follows the same distribution as old data. So that means basically assuming there is some pattern in the world. Generalizing well even when distributions change or that pattern changes is much harder and much much less well understood. Yeah. Um. Yeah, that's fair. All of the standard theory of statistical inference you've learned presumes that you have a model which was fixed in advance of seeing the data. If you use the data to select the model, that theory becomes invalid and it will no longer give you the correct p-values for hypothesis tests. So don't peek into your test data. Okay. All model selection methods we've assumed or we discussed aim at getting models which predict well. This is not necessary, and this is a very important point to highlight that people often forget. This is not the same as getting the true theory of the world. This just means you have a theory that explains as much of the world as you see very well. Again, that also gets at the causality behind machine learning, which, as you all know, is not a very well understood topic for good reason. Because people are excellent at making predictions these days, but they are still not able to back those predictions up with reasoning. Yeah, the last two items, selection with inference and parameter interpretation, deserve elaboration. So, at this point, we've seen a lot of inferential statistics. But of course, if you do model selection, the model you do inference with then is not fixed in advance, but is actually a function of data. What happens then? This depends on whether you do inference with the same data set you used to select the model or with another independent data set. If it's the same data, then all of the inferential statistics become invalid. None of the calculations of the probability on which they rest are right anymore. Typically, if you select a model so that it fits the data well, what happens is that confidence regions become too small. As do p-values for testing hypotheses about parameters. Nothing can be trusted as it stands. The essential difficulty is this: your data are random variables. Since you're doing model selection, making your model a function of the data, that means your model is random too. There is some extra randomness in your estimated parameters, which isn't accounted for by formulas which assume a fixed model. This is not just a problem with formal model selection devices like cross-validation. If you do an initial exploratory data analysis before deciding which model to use, and that's generally a good idea, you are yourself acting as a noisy, complicated model selection device. This is true. So, what he's trying to say is he's highlighting on this point of staring at your data before you're actually training your model. And he's saying that the bias you develop, that is also a model selection procedure. You are also saying that, okay, I think this data will definitely not be fit by a linear model. I think I need a quadratic, and I think this and that and whatever. So that's why you are acting as a noisy, complicated model selection device. And mathematically, the statistical inference that you draw from then on is not valid, like the calculation of the probability. And it's not easy to grasp this concept, so I will probably highlight. Yeah, I'll upload a more detailed set of notes about this. I don't know what happened to my old ones, or if I've been through this. I don't know. Okay, so 3 main approaches of post-selection inference. Ignore it. This makes sense. If you don't really care about doing inference, just select the model. You just care about what model is selected. Otherwise, I can't recommend. Okay. Beat it with more statistical theory. There is a lot of interest among statisticians in working out exactly what happens to sampling distribution under various combinations of models, model selection methods, assumptions about true data generated processes. We'll pass it by with some references. And 3 is evade it with an independent data set. Remember that if the events A and B are independent, then now set A is equal to the confidence set we calculated from the new data, covers the truth. B is equal to the model we selected from this old data was such and such. So long as the old and new data are independent, it doesn't matter that the model was selected using data rather than being fixed in advance. Yeah, what he's saying is staring at your training data won't matter as long as your test data was independently selected. Note that this means the validation sets, uh, in standard validation you keep your data aside, but this then when you're doing k-fold cross validation you're using all of your original data for validation. So then in that case it's not a good idea to stare at your data in advance, because effectively you are looking at test data. If you think that's incorrect, please correct me. Yeah, this is true, but you're not training models independently. So what I was saying was, if you as a human being look at the data, you know its distribution, and then that data that you've seen is going to be a test set at some point. So in that sense, yeah, 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 yeah. Okay. Um, of course, if you only use a portion of your data, whatever, blah 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 blah. I should really read this in more detail, but um, I will say that if there is doubt, if there is any question arising about this, please ask it on the group. But I will try to build a summary of this and paste it there, or at least make notes and upload it, so that makes sense. Yeah, but I'm going to leave this part for now. I just don't want to explain things wrong. That's it. Okay, this seems to have interesting exercises. Yeah, any questions so far? Mm-hmm. 3.5.1, yeah. Yeah, okay, so to repeat your question, just for the mic, if you if you look at the data and then train a model on it, it is saying that the confidence of your model in the data will be very high. Yeah, but this is the notion he tries to break down, is what I think, because he says the model will think it has high confidence, but in reality, because you have seen the data and accordingly pre-selected your model, that confidence region is too small, and therefore confidence is actually lower in reality than the model, or than you think the model has. Yeah, I think this bottom footnote highlights it. But again, this was like from 5 minutes of reading, so correct. The model will give a higher confidence, which is not the true confidence, because nothing can be trusted as it stands. Correct. I mean, the philosophical analogy, not the statistical one. Like, statistically, they're both different things. Um, but you can say that, yeah, the same way that your in sample error makes you believe you can do much better on out of sample data, this will confidence interval would make you believe you can do much better than you actually would. Hmm. Any other questions? Okay, seeing none, I will first stop voice recording. I have to figure out a good recording software, man.